That was it for central directory servers. The next couple of charts here is on connection networks or virtual routing nodes. Why are virtual routing nodes important? Virtual routing nodes allow you to minimize the link definitions between nodes and still get meshed connectivity between nodes so that there are no nodes playing intermediate routing on the session path, right? So let's give an example here. We've got a network over here where we've got one network node and 3 end nodes, and we want to know how many links it takes to mesh connect these guys. Well, if each node defines a link to the other node, then each node, there were 4 of them, would have to define 3 other links, one to each of the other nodes. So that's 4 nodes defining 3 links each, which means 12 links basically. If you add a 5th node to this picture, then it would be 5 nodes defining 4 links each, or 20 links. And if you define more, like n nodes to this picture, then you would basically have n times n minus 1 links. And what you see is, as the number of nodes you add to the network grows, the number of links you have to define grows exponentially. And nobody wants to do that. As their network grows, their definitions get even worse. So what virtual routing node does is allows you to define a virtual node in the middle, which you give it a name, and it looks like a network node in the topology database, although it looks like a virtual network node. And now, instead of each node defining a link to every other node, each node will define a link to his network node server so that he can get CP/CP sessions, and a link to the virtual node. And the topology database can see when 2 end nodes, for example, are attached to the same virtual node. And he knows that if he calculates a route through that virtual node, it's not really a 2-hop route, it's really a 1-hop route, because the virtual node doesn't really exist there. And on these definitions, we provide all the signaling information that any of the 2 nodes would need to be able to dynamically create a connection to the other node. And that's what basically connection networks are all about. You define your link to the virtual node, and now when you calculate your route, you automatically get a link from end node A, for example, or end node B to end node C, and you didn't have to predefine that connection at all. So this picture then, if 4 nodes want to define links to only 2 other nodes each, then they only have 8 links that you have to define for 4 nodes. And if 5 nodes only have to define links to 2 nodes each, we're talking about 10 links. But more importantly, if you have n nodes in the network, we have n times 2 links, which means as the number of nodes increases, the number of links increases only in a linear fashion rather than in an exponential fashion. So this keeps the number of links definitely in a manageable situation. But there's another reason that virtual routing nodes can be advantageous. And that is when you add a 5th node. If you added a 5th node to this configuration, you would actually have to go into each of the other 4 nodes and create that 5th link definition as well. When you add a 5th node to the bottom configuration, you may have to go into the network node to define the link to the end node, or you can have him configured to just accept dynamic connections coming in, which makes no change at all on the network node. You would clearly have to define the link that the new end node, for example, has to the network node, and the link that he has to the VRN, but no other changes are required in the other nodes in order for you to get mesh connectivity to the new end node automatically. So it also improves the ability to extend your network. It makes system definition a lot easier when you add nodes, because there's much less coordinated definition between the nodes. Just like with interchange node implications before, we had interchange node implications when we were doing HPR out of an interchange node, and the first hop happened to be through a virtual routing node. But basically, if you pretend the virtual routing node is not there, it's there when you calculate the route, but really there's only one dynamic link that's brought up between these 2 guys, so it really looks a lot like the previous picture. And so the bottom line again is, if the session starts on the interchange node and goes into APPN, we can do RTP end-to-end with a single RTP pipe. But if the session starts in the subarea network and goes through an interchange node into APPN, then we have to start this little 1-hop RTP pipe next to the interchange node, which in this case is actually a 2-hop RTP pipe because it's through the virtual node to the next physically adjacent node. And then from that node again, we can start another RTP pipe all the way to the rest of the, across the rest of the APPN session path, again, unless you've got an interchange node on the far side. I want to re-emphasize this important note that when you do interchange nodes with V1R10 and later, there is that coexistence issue that may require you to put additional APARs on previous releases and or install the new function APAR on V1R10 and later releases so that you can basically disable the HPR system function and eliminate the coexistence requirement. All right, so recommendations for connection networks. We recommend that you use them whenever it's possible because it allows you to minimize the link definitions, simplifies the job of adding new nodes, but it also allows you to achieve optimal session paths without any nodes playing intermediate network node routing. On end nodes, network nodes, and migration data hosts, you can use any type of connection network that you want because it's independent of the ZOS COM server release. On interchange nodes, though, you have to be worried about some of those previous restrictions that I was talking about. If you're still running pre-V1R4 COM server interchange nodes, then basically we did not have the function that allowed you to do HPR next to subarea through a virtual routing node. So if you still have V1R4 nodes in the network, you may have to define connection networks that support the ISR routing function, not just the connection networks that support only the HPR function. So you could still use, for example, token ring and X25, but if you're running pre-V1R4 VTMs, then you probably need to predefine, you probably can only predefine the EE links, the HPR only links, you have to predefine the links from the interchange node out to these nodes, rather than using a connection network to dynamically create them. This typically is not a stretch, because typically your interchange nodes are the network node servers for your end nodes anyway, so you have to predefine a connection for your CP/CP sessions anyway. But just keep in mind, if any of your VTMs are pre-V1R4, you may have to worry about being able to support the HPR next to subarea function through a virtual routing node. Okay, before we go on to some of the other functions like DLUR, DLUS, branch extender, and border nodes, we have to spend a little bit of time talking about the APPN sessions and services extensions, what they are, what their impact is on the APPN network. APPN was originally designed for LU62 sessions only. It was originally invented by System 36 and System 38 as a way to start LU62 sessions between two System 36 or System 38 nodes without the assistance of a VTM in the middle. That was the idea. So all sessions were primary LU initiated sessions. They didn't have to worry about things like slew initiated sessions, terminals logging on to applications. They didn't have to worry about log apple sessions or auto logon. They didn't have to worry about closed as path applications. They didn't have to worry about the request type sessions where you're doing printer sharing. They didn't have to worry about sessions that were queued because one resource was not available or because one resource was below session limit. That was the original APPN architecture that was done by System 36 and System 38. In order for VTM to play in an APPN network, we have to be able to do closed as pass, we have to be able to do sim log on queue, we have to be able to do the rel-rut functions. So all these functions that were not supported in the base architecture had to be supported before VTM could fully participate in an APPN network. So the first step toward doing VTM's APPN function was inventing the APPN session services extensions architecture, which are those extensions that allow all of these functions to work across an APPN network, so that when you migrate from subarea to APPN, your applications can do all the things that they used to do seamlessly without having to worry about there being an APPN network down below here. So we first created the APPN network, session services extensions way back in the late 80s, and we used them in the very first release of VTM that did APPN, which was VTM v4r1. It was an optional power on top of the base end node or the network node function. We extended the architecture to support all of those existing subarea functions to make it seamless again. Most of our APPN products, though, did not want to write all of the extra code that would be required to do these session services extensions. And since they only supported LU62 sessions, there was really no need for them to do that. So the new architecture that was invented went to great lengths to make sure that base APPN products that don't support the APPN SSE functions would still coexist in the network, and basically the APPN SSE capable nodes would have to detect when they're there, decide what they can and can't do, and basically compensate for them. That's basically the idea. So the session services extensions were invented by VTM for VTM, but they should have little impact on the existing APPN products and their ability to function in an APPN network.